Good morning, students. Welcome you all for this GATE class presented by Erode Sengunthar Engineering College, Tamil Nadu, sponsored by AICTE PRERANA scheme for preparing SC/ST students for higher education. In today's class, we are going to see about digital modulation schemes from the subject communications. Let us first see about the outline of today's class from digital modulation. First of all, we are going to see about introduction about the topic and information capacity, bits, bitrate and baud rate, and what is M-ary encoding, and digital modulation techniques like ASK, FSK, PSK and QAM, and some example problems related to GATE. Let's see the introduction of this topic. Okay, what is analog modulation and digital modulation? So initially, analog modulation and digital modulation systems use analog carriers to transport the information signal. So carrier is same in both analog and digital modulation systems. So both uses analog carriers to transport the information signal. In analog modulation, the information is analog. That is what the message we are using is analog form. Whereas with digital modulation, the message is digital. So the information is digital, which could be computer generated data or digitally encoded analog signal. So this is the basic difference under analog modulation and digital modulation. So digital modulation is the transmission of digitally modulated analog signals between two or more points in a communication systems. So it can be propagated through Earth's atmosphere and used in wireless communication system. So digital modulation offers several advantages over traditional analog system, so that we are using digital modulation techniques in present: ease of processing, ease of multiplexing, and noise immunity. So these are all the advantages of digital modulation over the traditional analog system. And applications are some of the applications: low speed voice band data communication modems and high speed data transmission system, and digital microwave and satellite communication systems, and personal communication systems. So what is the need for digital modulation? Why we go for digital modulation techniques? So initially we used analog modulation. The digital modulation allows improvement in the signal to noise ratio as compared to analog modulation scheme. So various advantages are present in digital modulation scheme, such as ease of error detection and error correction. Compared to analog, in digital we can easily detect the errors and we can correct the errors. So it's improvement in signal to noise ratio compared to analog modulation schemes. And also data compression, source coding and decoding is simpler in digital modulation compared to analog. So these are all some advantages and forms of digital modulation schemes. So in today's class, we are going to some basic forms of digital modulation schemes. So these are ESK, FSK and PSK. ESK is amplitude shift keying, FSK is frequency shift keying and PSK is phase shift keying. So these are all the basic digital modulation schemes. And another one is QAM, that is quadrature amplitude modulation. Let us see what is the digital modulation schemes one by one. Let us consider this equation V of t equal to V sine 2 pi f t plus theta. So in this, capital V denotes the amplitude of the carrier. So when amplitude of the carrier is varied in proportional to the information, that is message signal, then we are getting digitally modulated signal, that is known as amplitude shift keying method, ASK. So in analog, we usually call it as amplitude modulation, frequency modulation, like that. So in digital, we are using shift keying. So because with digital signals contains binary data, that is ones and zeros, so we call it as shift keying method. And next one is, if frequency of the carrier is varied proportional to information signal. When we are getting digitally modulated signal, so it is known as frequency shift keying. If the phase of the carrier is varied proportional to the information signal, then the modulated signal is called as phase shift keying. If both the amplitude and phase of the carrier are varied proportional to the information signal, so this one is quadrature amplitude modulation. So we are getting digitally modulated QAM signal. So here we are using both amplitude and phase modulation. So these are all the basic digital modulation schemes. So diagram shows the digital modulation schemes ASK, FSK and PSK QAM. The first analog message is converted to digital code. Then digital message ones and zeros is represented by pulse. So this digital message is modulates the sinusoidal carrier. So in digital modulation, carrier is sinusoidal signal. So and finally we are getting digital modulated signal in various forms. First one is ASK, where amplitude of the carrier is varied. So you can see in this diagram, amplitude is varied for the every binary data. And in FSK, frequency is varied and PSK, phase of the carrier signal is varied. In quadrature amplitude modulation, so in the last waveform, you can see both the amplitude and phase is varied. So this is the simplified block diagram of a digital modulation system. So this represents the digital communication system. So we are considering a transmitter and receiver. So this is the digital modulation scheme. So we are using digital modulator. So initially we are using precoder and digital modulator, and carrier is analog. So precoder involves the level conversion process and coding. Then the digital signal modulates the analog carrier, and it is filtered and amplified and transmitted through the channel. And at the receiver side, we are using demodulator and decoder for getting the original information signal. Let's discuss some of the terms related to digital communication system. It is information capacity, bits, bitrate, baud rate, and M-ary encoding. So first, information capacity. Information capacity is the measure of how much information can be propagated to communication system. How much information can be propagated, and it is a function of both bandwidth and transmission time. And bitrate is the number of bits transmitted during 1 second, bits per second. So every digital symbol is represented as binary digit or bit. Now, regarding information capacity, it is a very important formula, Shannon's formula. It is given by channel capacity also. So I equal to information capacity is given by B, that is bandwidth, and log to the base 2 and 1 plus S by N. S by N is the signal to noise power ratio. So information capacity is proportional to bandwidth and the signal to noise ratio. And we are using in log to the base 10, formula is 3.32b log to the base 10 1 plus S by N. The higher the signal to noise ratio, then we are getting better performance and higher the information capacity. And another one important concept is Nyquist sampling rate. Fs is equal or greater than 2 Fm. Fm is the maximum frequency. Fs is greater than or equal to 2 Fm. So this is a very important equation. Fs is the minimum Nyquist sampling rate and Fm is the maximum analog input frequency. Let us see an example. For a digital message, sequence is given as 1101, 1100, 1010. Sketch the waveform for the following. So this is for our understanding. We can sketch the waveform for ASK, FSK, PSK and QAM from our understanding of the digital modulation signals. So we can sketch the waveform from this diagram. For 1 0 and 1 0, ASK is drawn by varying the amplitude of the signal like that other digital modulation schemes. So you can practice to draw the different waveforms of digital modulation scheme for understanding the basics of digital modulation schemes. So next example, by using Shannon's formula, calculate the information capacity if signal to noise ratio is 30 dB and bandwidth 2.7 kHz. So we have seen the Shannon's formula for calculating the channel capacity or information capacity given by B into log base to 1 plus S by N. And if you are using another formula, that is 3.32 B log base 10 1 plus S by N. So here we are substituting bandwidth 2.7 kilohertz. So it is 2700 and signal to noise ratio 30 dB. It is given in decibels. So its value, signal to noise ratio value can be substituted from this. Decibel value is converted into signal to noise ratio value by using 10 log 10 and taking anti-log of the 30 dB, we can get 1000. So if we are substituting, then answer is 26.9 kilobits per second. So this is the information capacity calculated from Shannon's formula. Next example, determine the Nyquist sample rate for a maximum analog input frequency 7.5 kHz. So we know well Fs should be greater than or equal to 2 Fm. So Fs is greater than or equal to 2 into 7.5 kHz. So we are getting 15 kHz. So this is a Nyquist sample rate for the given input frequency. Okay, next let us see what is M-ary encoding. So it is advantageous to encode a level higher than the binary where there are more than two levels or two conditions are possible. That is, if we are considering more than two conditions or more than two levels, we are using M-ary encoding. For example, if the number of bits necessary to produce a given number of levels is expressed as number of bits represented by capital N and number of levels or number of conditions is represented by capital M. So the relation is N equal to log base 2 M, or M is represented by 2 power N. So if we are using 2 bits, we can represent 4 levels. If we are using 3 bits, then we can represent 8 levels. So this is the M-ary encoding concept. Each symbol represents n bits and has m signal states. Example, a digital signal with 4 possible conditions or voltage levels frequencies is an M-ary system with number of possible conditions m equal to 4. So if the system is represented as M-ary system, if there are 4 possible conditions or levels, then m equal to 4. So in this example, find the number of voltage levels which can represent an analog signal with first one 3 bits and 8 bits and 2 bits. So we know the M-ary encoding concept. So number of bits is given. We can calculate the number of levels, 2 power n formula. So correspondingly 2 power 3, 2 power 8 and 2 power 2. Next one is Baud. Baud refers to the rate of change of signal on the transmission medium after encoding and modulation have occurred. So it is a symbol rate. So Baud refers to the symbol rate, number of symbols per second after encoding and modulation. So it is very important in digital communication system to represent a Signal after encoding and modulation. The symbol rate or rate of change of signal on the transmission medium. So it is given by 1 divided by Ts. Ts is the time of the one signaling element or symbol. So it refers to the symbol rate. We are comparing bitrate and baud rate. Bitrate refers to the rate of change of digital information, which is usually binary. It is represented in bits per second. And baud rate also a rate of change, but it refers to the rate of change of a signal on transmission medium after encoding and modulation process. So this is the difference between bitrate and baud rate. And next term we are going to see is minimum bandwidth. So bandwidth is the important parameter when considering the digital communication system. The minimum bandwidth refers to the minimum bandwidth necessary to pass the M-ary digital modulated carriers. To consider the equation Fp equal to B log base to M. Here Fb refers to channel capacity in bits per second. B is the minimum Nyquist bandwidth. Number of discrete signal or voltage levels represented as capital M. So minimum bandwidth can be represented as B equal to Fb divided by log 2 base M. It is also written as F by N. N is the number of bits encoded into each signaling element. To determine the minimum bandwidth and baud necessary to pass 10 kilobits per second binary signal using amplitude shift keying method. So we are going to calculate minimum bandwidth B equal to Fp divided by log 2m. The formula can be written as Fp divided by N. So consider amplitude shift keying. So in amplitude shift keying, we must substitute N equal to 1. When we are substituting N equal to 1, bandwidth equal to 10,000 divided by 1, given 10 kilobits per second, and substitute N equal to 1 for amplitude shift keying. So it gives 10,000, which is equal to baud rate. So in ASK, minimum bandwidth is equal to baud. Additional note, what we note here is N equal to 1. Here 1 bit is represented for a signaling element or symbol. So in ASK method, we are using, that is amplitude shift keying. Amplitude is varied according to the digital information. So for every binary digit, that is 1 and zeros, we are representing the 1 bit data. So here N equal to 1. So in binary system, baud is equal to bits per second. So both are equal. In higher system, bits per second is always greater than baud. So digital modulation techniques. 4 basic digital modulation techniques that are amplitude shift keying, frequency shift keying, phase shift keying, and quadrature amplitude modulation. Okay, let us discuss about digital modulation techniques one by one. First one is amplitude shift keying. So it is the simplest digital modulation technique where binary information signal is directly modulates the amplitude of the analog carrier. So in this ASK, there are only two output amplitudes are possible according to binary data. The binary information signal directly modulates the amplitude. So it is also called as digital amplitude modulation. It is represented in this equation as amplitude shift keying wave. It is written as 1 plus Vm of t, that is digital information signal, and A by 2 is the unmodulated carrier amplitude, and omega c is the, in this term, cos omega ct. Omega c represents the analog carrier frequency in radians per second. The modulating signal here is the normalized binary waveform. So here we can see the binary input and digitally amplitude modulated output. So when logic 1 is to be transmitted, then Vm of t is plus 1 volt. Then ASK output is A cos omega ct. It represents the capital A represents the ASK wave amplitude. And when logic 0 to be transmitted, Vm of t equal to minus 1 volt. So when we are substituting Vm of t in previous equation, we get 0. So amplitude is varied according to the digital data. Next method is frequency shifting. It is a simple digital modulation technique. Here binary signal that varies between two discrete voltage levels rather than continuously changing analog waveform. So here it is represented as binary frequency shifting. So ASK, FSK, del F, it means shift in carrier frequency. So it is an important parameter in FSK. It is proportional to amplitude of the binary input signal. So in this equation, del F is used in this cosine term. So it is given by Vc cosine of 2 pi Fc plus Vm of t. So Vm of t represents the binary input signal in volt and del F is the shift in carrier frequency. Here we can see the FSK output corresponding to digital data. So when logic 1 is transmitted, Vm of t value is plus 1. So when we are substituting in this equation, we can get 2 pi in cosine term, 2 pi Fc plus del F into t. In digital data 0 to be transmitted, then Vm of t equal to minus 1. Then cosine term is 2 pi into Fc minus del F into t. So it is represented in this diagram. Shift in carrier frequency is denoted as plus del F. So it is the maximum higher frequency or mark frequency FM. When it is minus del FF, then it is represented as lower frequency or space frequency. So corresponding to digital data, logic 1, then FSK output is represented at higher frequency or mark frequency, and logic 0, it is represented as lower frequency or space frequency. So we can relate this using this equation del F equal to modulus of Fm minus Fs divided by 2, where del F is frequency deviation in hertz and the modulus of Fm minus Fm is the absolute difference between mark and space frequency. In this diagram, we can represent binary input and corresponding FSK output. It is shift in analog carrier frequency is represented for every digital data. Here in this diagram, Fs represents the space frequency and Fm represents the mark frequency. So when we are giving binary input as 0, then frequency output is space Fs and binary input is 1, and frequency output is mark frequency Fm. Baud for FSK is determined by setting n equal to 1. So Baud for FSK is Fb divided by 1, which is equal to Fb. So in this example, we can calculate FSK values for an FSK signal given a mark frequency 49 kHz and space frequency 51 kHz and input bitrate is given as 2 kilobits per second. So previously we have seen the FSK frequency plot and peak frequency deviation. So we are going to determine peak frequency deviation, minimum bandwidth, and Baud for a binary FSK signal. So recall the formula for peak frequency deviation and minimum bandwidth and Baud for FSK. So peak frequency deviation is given as del f is equal to modulus of Fm minus Fs. So in this problem, we are given with mark frequency 49 kHz and space frequency 51 kHz. So we are substituting those values divided by 2. Then we are getting del f as 1 kHz. And to get minimum bandwidth, we should use these values, that is del f 1 kHz. So when you are substituting in minimum bandwidth, B equal to 2 into 1000, that is 1 kHz is substituted here, 1000 plus input bit rate, that is 2000. It is given in the problem. So answer is 6 kHz for minimum bandwidth. And Baud for a binary FSK signal. For FSK n equal to 1, so Baud is its bit rate, so that is 2000. So next, another digital modulation scheme is phase shift keying, PSK. So it is a form of angle modulated constant amplitude digital modulation. So here the amplitude is constant, the parameter going to be varied is phase. So binary digital signal input and limited number of output phases is possible. For example, simplest PSK is binary phase shift keying. Here two output phases are possible, so it is given as M equal to 2. Two phases possible for a carrier with one phase for logic 1 and another phase for logic 0. So here output carriers between two angles separated by 180 degree. So in this binary input is given as logic 0 and logic 1. The output two output phases are possible. One is 180 degree and 0 degree. And it is represented in this phasor diagram. So logic 0 here represented at 180 degree and logic 1 is represented at 0 degree. And also constellation diagram. So here logic 1 and logic 0 and output phases are represented at this corresponding points. So here we are seeing BPSK transmitter where binary data input is given and it is level converted into polar format, and it is given to balanced modulator where analog carrier frequency input is given. So it acts as a phase reversing switch. So we are getting two output phases from this BPSK transmitter. According to digital data, so carrier shifts between 180 degree and 0 degree. So that is the BPSK signal modulated output. So at the receiver of BPSK, the input signal is given as plus or minus sin omega ct. Because two output phases are possible, so that plus sin omega ct or minus sin omega ct, and it is filtered and demodulated, and finally binary data is obtained from the circuit. So previously we have seen the constellation diagram of PSK. So it is an important diagram in the digital modulation subject. So it defines as a graphical representation of the complex envelope of each possible symbol state. So in this, x-axis represents the in-phase component and y-axis represents the quadrature component. It is an example for constellation diagram. So variation of phase is represented and also amplitude is represented here as magnitude So from the origin it is represented at the point S and the phase is represented from the x-axis. So this the x-axis represents the in-phase component and y-axis represents the quadrature component. So this is another example of constellation diagram where n equal to 3 and m equal to 8. So 8 possible levels. So 8 possible levels are represented at 8 different phases in this diagram. So next we are going to see about quadrature amplitude modulation. Here it combines both amplitude and phase shift keying methods. So here both the amplitude and phase of the signals changes. So it is used in voice band data transmission. QAM is also equivalent to 4 PSK, 4 level phase shift keying. So this is the constellation diagram of 16 QAM. So here 16 states are possible. So different states are represented using both amplitude and phase variation. So it combines both amplitude and phase shift keying. The main advantage of quadrature amplitude modulation is it is very much bandwidth efficient. So in the digital communication, we are considering very important parameters are one is bandwidth and another one is transmission power. So bandwidth requirement, I mean considering the phase shift keying, that is binary phase shift keying, there are only two output phases are possible, either 0 degree and 180 degree. So we can represent only 1 bit per symbol. But in when considering the QPSK, that is quadrature phase shift keying, there we can represent 2 bits per symbol. So we are combining 2 bits, combining successive bits. So when we're coming to 16 QAM, that is quadrature amplitude modulation, we can combine several bits. For example, in 16 QAM, m equal to 4. So here it is a it gives bandwidth efficient. So 16 QAM has the largest distance between points but requires very linear amplification. So higher level M-ary schemes are very much bandwidth efficient, but the another factor should be considered is so these schemes are susceptible to noise. Bandwidth efficiency is used to compare the performance of digital modulation techniques. So it is defined as ratio of transmission bitrate to minimum bandwidth. So let us see an example. In a digital communication system, the bitrate of NRZ data stream is 1 megabits per second and carrier frequency of 100 MHz. Compute the symbol rate of transmission and bandwidth requirement of channel for BPSK and QPSK system and compare the result. So we are going to calculate the symbol rate and bandwidth requirement separately for BPSK and QPSK systems. So in BPSK, the calculation of symbol rate is given as 1 by Ts. That is Ts is the symbol duration. It is equal to bit duration in BPSK. Ts is equal to Tb, that is given as symbol duration and bit duration are same. So symbol rate is defined as 1 by Ts, which is equal to 1 by Tb, which is equal to bit rate. So that is given as 1 megabits per second. And bandwidth requirement of the channel for BPSK system is given as 2 times the input bit rate. That is 2 into 1 megabits per second, so we are getting 2 megahertz. So this is calculated for BPSK system. So for QPSK, quadrature phase shift keying, Ts is equal to 2 TB. So symbol that is 2-bit duration. We are considering 2-bit duration. Here we are combining 2 bits per symbol. So symbol rate is given as 1 by Ts, which is 1 by 2 TB. So Fp divided by 2. So 1 megabits per second divided by 2. We are getting 500 kilobits per second. And bandwidth is given by input bit rate, that is 1 megahertz. So when we are comparing these two results, previously for BPSK, we have obtained symbol rate is 1 megabits per second and bandwidth is 2 megahertz. And here QPSK, symbol rate is 500 kilobits per second and bandwidth 1 megahertz. So when we are comparing these two results, bandwidth required by QPSK is half compared to BPSK, and symbol rate of QPSK is also half compared to BPSK. The QPSK, that is quadrature phase theme, here we are combining two successive bits in the data sequence. Two successive bits are combined, and after modulation it is represented by two output phases. But in BPSK, there were only two symbols in BPSK. Phase shift occurs in only two levels. But in QPSK, there are four levels of output phases are possible. So this reduces the signaling rate. So symbol rate of QPSK is also half compared to BPSK. So we can understand this from this example. So next example, consider the baseband pulses at the rate of 2400 bits per second are transmitted over telephone channel using Nyquist first criterion and roll-off factor of 12.5 percentage. The 16-point QAM is used to estimate the bandwidth before and after modulation. So what we are going to calculate here is the bandwidth before modulation and after modulation. So first we are considering bandwidth before modulation, and let B not be the bandwidth without rise to cosine spectrum. So we are not considering roll-off factor here first. So B naught is it is equal to bit rate, that is 2400 bits per second. Next, bandwidth using rise to cosine spectrum with roll-off factor. So roll-off factor is given in this problem as 0.125. So when we are substituting in this B naught into 1 plus alpha, 2400 into 1 plus 0.125. So we are getting bandwidth before modulation is 2700 Hz. So next, to obtain the bandwidth after modulation. The modulation here we are using 16-point QAM. That is 4 bits per symbol. So for QAM, bandwidth B naught is given as B naught is equal to 2fp by n. So this is the bandwidth formula for quadrature amplitude modulation. For 16 QAM, we are using 4 bits per symbol, so n equal to 4. So substitute this, n equal to 4 becomes B naught is equal to 2 into 2400 bits per second divided by 4, so 1200 Hz. When we are using a rise to cosine spectrum, substitute roll-off factor value. So B equal to B naught into 1 plus alpha. So substituting B naught value and alpha 0.125, we are getting 1350 Hz. So in this problem, we have calculated bandwidth in two different phases. So here it is 2700 Hz before modulation and 1350 Hz after modulation. So bandwidth is reduced to half with 16 point QAM. So we know well that quadrature amplitude modulation is bandwidth efficient. Okay. In today's class, we have seen the introduction of the digital modulation schemes ASK, FSK, PSK, and also quadrature amplitude modulation and some of the examples for digital modulation schemes. Okay, thank you all. Thank you, students.